Hey guys, welcome to lecture number 12. Well, let me tell you something about this lecture. Probably you were a bit surprised when I sent you the email that I didn't include a video. Well, even I was surprised because I did not remember perfectly what I did last fall, but I did not do a separate video for the chain rule, the thing that we'll cover today. Because I thought, okay, I will do it just by, I'll cover it along with the implicit differentiation, but this time I decided differently. So I decided to do a video especially on the chain rule because I want you to see how you will apply this technique in the lecture that will follow next, which will be about implicit differentiation. And I say, why not cover this? All right, so let me get started. So I will explain immediately. In fact, even last lecture, I don't know if you, so this is the lecture. So the chain rule. Last time, I even said something, but I didn't quite say it explicitly. When we took the derivative of cosine of pi times t, or sine pi t, and there was that constant inside, and we took that constant out. Well, it was kind of, I hope you, well, okay. So I hope that, well, I'm experiencing some problems here, but anyway. Okay, let's get started. So today we'll talk about the chain rule. So let's see what is this all about. Let me just dive directly into the subject. All right, so the chain rule and composite functions. So I remember I told you about the composition of functions, right? Let me just say something about it. So remember when we had the composition of functions, right? It was something like this. Man, this is getting annoying. So we had f of g of x, right? And remember, this was nothing else than just f, we compose f with g and of x. Right? And you see, you have two functions, and then you take the argument will be one of them. So in other words, if you look, this is what the chain rule is going to be all about. And let me just, I would like you to look at these examples. So the chain rule deals with composite functions and adds a surprising versatility to the rules previously introduced. And I would like you to look at them and look in the first one here, without the chain rule, y of x. So keep in mind that this y here is a function of x. So I'd like to say this, and the same here. But also, if you look at the first function, let's say y equals x squared plus 1, it's just the way it is. It's like a square, x squared plus 1 is a quadratic function. It's given explicitly. But if you look on the right-hand side, you have y of x equals the square root of x squared plus 1 here, you see? And I would like to ask you, what is the difference between the two? Can you tell me that? I mean, the first obvious difference between the two, what is it?
The square root around all of it.
Aha, so it's the square root around it. Okay, let me ask you something. can you see the function, the square root function? Can be this written in terms of the function? All right, let me be more explicit. Can you write the function on the right in terms of the function of the left? Can you see the, can you, okay, even more specific, can you tell me if it's the composition of, the function on the right is the composition of the function of, from the left with another function? Based on what we said here? Yes, okay. What would those functions would be?
Y equals root x and y equals x squared plus 1.
Exactly. So is the composition, okay, let's use some other, so let's just say here that with this y of x is what? Is f composed with g of x. And who is f of x? Who is g of x? Tell me.
F of x is root x.
Exactly. And g of x is?
X squared plus 1.
Exactly. You see? Is f is x squared plus 1, which you find it here. So that's the difference between the two. All right, beautiful. Let's see, what about the second one? Can you tell me the same thing about the second one? Is this guy here on the right the composition of something here from the left?
Yes.
Tell me. So y of x will be what? F composed with g of x, and f of x will be what?
3x.
Is 3x, and g of x is?
Cosine x.
Cosine x. Yes. Right? All right. And the same go with the others. These two, I'll leave them to you as an exercise to figure it out. Right? So this is how is the difference between the two. And now guess what? The chain rule will be nothing else than just about finding the derivative of the composition of the composite functions. So let's be, so decomposing composite functions. So let's see. I'd like you to, what's going on here? Okay, let me just take out this. So I would like you to look at the following functions. And think about it so I would like you to decompose these functions. So think about it for a minute or two. So let's see, for 1 over x and x plus 1, who is f, who is g? So, okay, let's write y of x is f composed with g of x, right, which is f of g of x. And I would like you to tell me, in this case, f of x is what? And g of x is what? And let's go with all the others as well. And let's write here as well. So let's see, for the first one, what do you think? So for the first one is what? F of x is what? Is 1 over x, exactly, like Jasper says here. So f of x is 1 over x, and g of x is x plus 1. Great, beautiful. What about the second one?
F of x is sine x, and g of x would just be 2x.
Exactly. And for the third one, I would like to hear somebody else. Not Kyle, maybe somebody else will answer. So what is f, what is g?
Is f the square root and g the actual function inside?
Exactly. So f is the square root of x, and g of x will be 3x squared minus x minus 1. That's it. This is how you recognize the composition of functions. I hope it's clear for everybody, right? So let me show you. Well, I used a different notation here, right, in my slides. So instead of g, I said u, but it's the same thing. So you can just, okay, say this is g. Let me put it like this, right? And the same here, right? So, all right, so that's it, exactly. So g is x plus 1, f of x is 1 over x, just like we said. Here in this case, f of x is sine of x, and g of x is 2x. And here f of x is the square root of x, and g of x is this quadratic function, 3x squared minus x minus 1. All right, so this is how we see the composite functions. And now I would like to go dive directly into the subject. And I would like you to look at the chain rule. Very, very, very carefully. Anyway, I'm just going to stick to the notation from the slides. I don't want to say G, but it doesn't matter. You can look at U as G and F for F. So in other words, if we have the composition here, F composed with U of X, which is given by F of U of X, which is this guy here, well, guess what? The derivative of F of U of X, so the derivative of that composite function, is nothing else than just the derivative of f of u with respect to u, pay attention to, with respect to the inner function, times the derivative of u with respect to x. So keep in mind that this function, this inner function, u of x, is a function of x. Or equivalently, if we want to write this, so I can write this as f of u of x, everything prime if you want. This will be nothing else than just what you see here. So it's, okay, let me write it again. F prime of u of x times this guy here, u prime of x. That's the rule. And I would like you to look at it very, very, very carefully. Again here. So that's the derivative of u of x. And of course, we can use this to, we would like to see how we will apply this chain rule for different examples, right? So keep this in mind, it's very important, this rule, right? So once again, if you have a composite function, f of u of x, then the derivative of f of u of x will be nothing else than just the derivative of f with respect to u, pay attention to the inner function, and times the derivative of u with respect to x. So you always keep in mind that the u of x is the inner function, the f of u is the outer function. So that's how you're going to keep this in mind, right? I hope this makes sense. Okay, now let's see some examples. And the first example that I have in mind is the following. Okay, you'll see the rule. So look here, find the derivative of this function. I'd like you to think of this problem for a bit. So first you need to identify which one is the outer function, which one is the inner function. So that's the first thing that you need to do. So let's see, we have some answers here. I see Jasper, Isha, sorry. This is how you pronounce your name, right? I hope Isha, right? Isha, okay, sorry. Yeah, you're right. Isha. Let's see. Okay, yeah, so let's see. So the inner function will be what? Will be that quadratic, not quadratic, that degree 4 polynomial over there, right? So it will be, so u of x is 3x to the 4th minus x plus 2. So that's the inner function. And the outer function will be f of u equals u to the 7th. And guess what? You have the rule here. Look at it. Look at this beauty here, right? So you have it here, so let's apply it. So once we apply this, we have the following. Guess what? Look. So f of u again is u to the 7th. So once we apply the chain rule, right? Here is the chain rule. So this will be the derivative, as you can see above. As you can see it here, right? This will be the derivative with respect to u of u to the 7th times the derivative with respect to x of u of u. So let's compute the derivative. So what is du over dx? Well, as you can see, the function there is what? It will be 12 x cubed minus 1. And what is the derivative? Du, no, sorry about that. So what is, oops. So now what is the derivative? So d over du of u to the 7th is what? Is 7u to the 6th, right? So that's the, and now let's see clearly here now, look at it. So you'll have 7u to the 6th, which is this guy here, times this guy here, 12x cubed minus 1, which you see it here, right? And now you just, you plug it in because you know who u of x is, right? Look at u of x. So this guy here, this is just u of x, right? And that's it, that's the derivative. That's the whole thing, right? Is it clear? Okay. Now let me give you another problem, a word problem. You would not expect this, but let's see. I want you to read the following statement. So, what does it say? So the budget for coffee depends on the number of cups consumed per day and on the price per cup. So the total budget changes if the price goes up or if the consumption goes up. So the example given is that during late night preparing for midterm exams, for example. So we would like to quantify the rate at which your budget for coffee would change if both consumption and price change. I thank God that this was not, instead of coffee was not put there like any alcohol or beer or something. So what do you think of this? When you see, look at this. So we need to quantify the rate, look here, at which your budget coffee would change. When you hear the word change, you think of derivative. But this time, you have something to take into account. And what would that be? And let me tell you explicitly now, how are we going, why the chain rule is very important. You see, this is a real life situation. So let's see, the total rate of change of the coffee budget is a product of the change in the price and the change in the consumption. So you see, you have two functions here. So let's identify these two functions for time t, and we take this time t, let's say in days. So we will consider y of as f of u, which will be the price of u cups of coffee. And of course, u, this the cups function, let's say, u will be a function of t, right, of the time, will be the number of cups of coffee consumed. So this is the price of cups of coffee. And now u of t is the number of cups of coffee consumed. So the number and the price, that's right. You see, before, and even if you look at the statement of our problem, what it asks us to do is to quantify the rate. When you hear the rate, you always think of derivative, at which your budget for coffee would change if both consumption and price change. So you have these two functions that change. So you have the number of the coffee consumed, so the number of the consumption, and also you have the price. So guess what? Chain rule will come into rescue, and here we go. So that's how we're gonna quantify. So du over dt will be dy over dt is dy over du times du over dt, which is nothing else than just f prime of u times u prime of t, right? So that's the chain rule here. Again, that's a nice way to put it, right? So in other words, let me just say explicitly, so the chain rule here, so if y is a function f of u, right, is a differentiable function, right, of u, and if u is a differentiable function of variable x, I'd like you to pay attention because they're, so y is a function of u, but also u inside is a function of x. So you see you have a composite function, u is a composite function. Then guess what? Y, which will be f of u of x, like I said, is a differentiable function of variable x. And guess what? By applying the chain rule, you'll have this. So this is the chain rule here. So d over dx of f of u of x is the derivative of f of u of x times u prime of x, which is written here explicitly, as you can see. It's the same thing here as here. The only difference is that the variable instead of t is x. So, but I'm sure you can cope with that. There's no difference. And now, guess what? Well, again, if we would like to, again, the chain rule, the derivative is this, right? Anyway, I don't want to lose time with the proof of this, but I would like you to remember this rule. You can actually find the proof in the notes, it's right there. I would like to stick more to applications. So again, this is the chain rule. So again and again, you will see the formula. Like I said, this will be very important. I would like to stress this again. This will be very important when we will talk about implicit differentiation. So the chain rule is critical for that. Okay, let's see. Any questions so far? Anything unclear so far? please, if there is anything not unclear, stop me at any time. Don't hesitate to stop me.
I think we're good.
Yes, Frank. Have questions? I heard something. Frank, no? Okay. All right, now I'd like to see examples because I would like to see more and more examples of chain rule. And the first example that I would like to draw your attention with is the following. I would like you to look at this guy. So look at this. There is a, okay, I don't want you to be confused with this guy. This is a circ here. It's not a dot, it's a circ. Okay, let me write it so that, because the dot you'll see that this is a product. No, it's a circ. So it's f of u of x prime of 3. So what do you think? Let's see. So let me recall the composition. Again, this is a circ here, right? F of u of x is f of u of x. F composed with u is f of u of x. And now let's apply the chain rule here. So let me write it here, just f of u of x and everything prime. This guy will be what? It will be f prime of u of x times u prime of x. And we like to see what happens when x is 3. So let's see. So again, this is a circ, right? I would like you to distinguish between the two. So f of, by the chain rule, right? Here we apply the chain rule. It's right here. So this guy will be f prime of u of 3 times u prime of 3. And now let's see which one is which one. You see u of 3 is somewhere here. U prime of 3 is somewhere here. So let's see. So this is f prime, because I know that u of 3 is 5, right? So this will be equal to f prime of 5 times u prime of 3. But now let's see. F prime of 5 is what? U prime of 3 is 7, and f prime of 5 is what? Is 2. So this would be 2 times 7, which will give us 14. So that's basically what we did. Did we use any other? So we used this guy here. Did we use f prime of 7? No, we didn't use, and we didn't use f of 3 equals 4. So you see, I was a bit sketchy here. I gave you extra information so that I can be a bit confusing. But like I said, you don't need too much information. You only need, when I'm asking you to find the derivative of this composition here, the only thing you need is what happens to f and u, to f prime of u and u prime. So, okay. All right, now let's see another example, which says the following, and I would like you to think of this guy. So we want to find the derivative of this. And again, you have the chain rule there. So So you see you have a fraction there, so you could see something. So what do you think? What are you tempted to do here? Because you have a fraction, so maybe you will be tempted to apply a power rule.
Decomposition.
Okay, say that again, Nolan.
Decomposition.
No, I didn't hear.
Decomposition.
Decomposition, right? Who is who? So who is the inner function? Who is the outer function? So u of x is what? Let's say, and f of x. So who is who? So which one would you consider the inner function? Let's see. So the outer function will be 5 over x over an x squared. Be more specific. Maybe 5 over u squared, but anyway, let's go with the inner function first. So the inner function will be, let's take 3x to the fourth minus x plus 2, right? And the outer function, let's change the color here so that you guys see it. I think it was with green. F of x will be what? 5 over u squared, right? Okay, that's exactly what we have here. Great. And now keep in mind that we need to use chain rule. Look at this guy here. The chain rule. So what do we need to know? We need to know the derivative of f with respect to u, pay attention, and also we need to find the derivative of u with respect to x. And let's see that. So this guy is nothing else by just identifying these two, the inner and the outer functions, is the derivative of 5 over u squared with respect to u, right? So that's the outer function. And now we would like to times the derivative of u with respect to x. And that will be the inner function. All right, beautiful. So let's do this. First, what is the derivative? Well, you can write 5 over u squared, and let me do that. I want you to. 5 over u squared is nothing else than just 5 times u to the negative 2. And the derivative of this guy will be 5 times negative 2 times u to the negative 2, negative 1, which is negative 10 u to the negative 3. That's the guy here. And look at it. You see it here. Boom. That's great. And now guess what? Let's write the derivative of u with respect to x. As you can see, it that's the function. So here, let's go. U prime of x is what? Is 12x to the cubed minus 1, which you see it here. You see? And that's it. And now what are you going to do? You're just going to plug in the function u. So the function u, let's do not forget who this is, as you can see it here, u of x. And that's it. That's the derivative. See it here, right here. That was it. It's just a straightforward application of the chain rule, but the only thing you need to look carefully at was to identify which one is the inner function, which one is the outer function. Does this make sense? Is everything clear for? No. just look at it a bit, because another example will follow, just in a similar fashion. Okay, let's see. Another one. Look at this guy. So we need to find the derivative of that square root over there. And as you can see, I have similar function. Again, I like to use the chain rule, but first you need to identify which one is the inner function, which one is the outer function. So tell me who u of x is, and also tell me who f of u is. So let me write them both here. Okay, let's start with u of x. Who is u of x?
Would it just be the 3x to the 4th minus x plus 2?
Exactly, 3x to the 4th minus x plus 2. And who is f of u?
Square root of x.
Exactly, square root of u, you mean. Right. All right, so I identify these two, and keep in mind that I want to apply the chain rule here. So let's do that. So I'm identifying these two functions, which is great. And now I'm going to use the chain rule. So once I identify this, as you can see, I'm taking the derivative. As you can see here, look, this guy here, it's this guy here, right? Because f of u is the square root of u. And now this guy here is nothing else than this guy here. But first, let's compute these two derivatives. So what would you do? For example, how would you compute? Okay, first of all, let's take care of the derivative of u. So u prime of x will be is what? Can you tell me? Well, it's the same function, but it is what? It's 12x to the cube minus 1. I already computed the derivative of this guy. But now I want to veer towards the derivative of the square root of u. How would you compute the derivative? So square root of u prime is what? How would you compute the derivative of this guy? So if you have square roots, what did we see earlier? In previous example, what did we see? Well, we had rationals, but even when we have square roots, wait, what? 1? No, I don't think so.
U to the power of 1/2.
Exactly. So it's why say that again? U to the power what? What power?
1/2.
So it's u to the power 1/2 prime, correct. Which will be equal to what? 1/2 times what? U to the power 1/2 minus 1. Or 1/2 times u to the negative 1/2, which if you want to write this in terms of radicals, as you can see it here, look at it. This would be 1/2 times u to the negative 1/2 would be 1 over square root of u. Or if you want, you can write this. And guess what? Look at it here, right? And if you go, as you can see, you look at this guy here. It's the same thing. Or you can leave it like this, or you can write it in terms of radicals. It doesn't really matter that much, but you can clearly see here inside, this is u of x, this function here. And clearly, right? And this is the derivative. So that's it. You see, again, this is just another application of the chain rule. Any questions about this example? Because we will continue with many examples. Okay, I hope it's clear. All right. If so, what about this one? So the derivative of sine of x squared, pay attention here, the argument is, I want to stress this out, is sine of x squared, so inside the function sine. So here, again, the same thing I would like to identify. So u of x, who is the inner function and who is the outer function f of u. So let's see, what do you think?
F of u is sine x, and then u of x is x squared.
Exactly. So u of x is x squared, and f of u, pay attention, is not sine of x, is sine of u, right?
Yeah.
So don't forget the argument here is u. All right. And guess what? By applying, let's see. And here, let me write the derivative. And what is the derivative of u? U prime of x is what? Is 2x. Exactly, 2x. And what is the derivative of sine of u? F prime of u is what? Cosine of u, correct. Okay, great. And now the only thing I need to do is just to apply, look at this guy here. This is the derivative, right? That you see here. And this guy here is the derivative of u that you guys see here. All right, let's do it. So identify these two functions here, the inner and the outer functions, as we have seen. And now we will apply, and guess what? So that's how we're going to write. So once we apply the chain rule, the guy here, the derivative of this is nothing else than just this guy here, cosine of u, as we have seen. And also the derivative of u with respect to x is this guy here, as we have seen here, look. Beautiful. But now do not forget who my function u of x is. So I need to go back to the argument. So this is nothing else, right? This is cosine here, and this is u of x. And this guy here is u prime of x. So that's it. Had enough? Not yet. More and more are coming. Let's see. Again, think of this example. So I would like to find this time the derivative with respect to x of this function, tangent of 3x to the fourth minus x plus 2. Probably I'm going to use the same function at this point. So now I would like to find the tangent, the secant, and maybe some others as well. So we're just going to deal with examples, many, many examples at this point. So again, let's identify who is the inner and who is the outer function. So let's see, u of x and f of u. First, let's go with u of x. Or maybe there are 3 of them, who knows? In fact, let me be more specific here. Let's see, Sabrina says something like this. Let me just to see on the chat. So she says, let's see, u of x is 3x to the fourth minus x plus 2. And f of u is tangent of u. Is tangent of u. Exactly. Yep, that's right. Yeah, that's correct. So by applying the chain rule here, exactly like also Frank says that. So in fact, the derivative, let's see here, the derivative, u prime of x is 12x cubed minus 1. And what is the derivative of the tangent? And here prime of u is what? The derivative of the tangent is what? Is secant squared of u. Ouch. Sorry about that. All right, so let's see. I'm again here, as you can see, the derivative, that's here. And also we have the derivative of u with respect to x. And here we go. As you can see, the secant comes out. Look at this guy here. That's this guy. And if you look at this guy here, is this guy. Right? And now you're just going to replace who u of x is, and there you go. Right? So this is, keep in mind that this is u of x here. And keep in mind that this whole thing here is u prime of x. Okay. All right, more examples. The same thing with the secant. So what do you think in this case will happen? So it's pretty similar, right, to the tangent one. Anyway, I'm gonna glance through this because it's pretty similar, right? So the outer function, the inner function, u of x will be the same. The outer function will be secant of u. It's just the same as the tangent, but this time we have secant, so we need to take care of the derivative of secant. And guess what? By applying the chain rule, now we need to take care of the derivative of secant, right? Of u, which we know what it is. What is the derivative of secant of u? Is secant of u times tangent of u, right? So secant, let me write it like here. Is secant of u times tangent of u. Okay. All right, let's look at it here. As you can see, this guy here, so this guy is this guy. And also now, here, if you look at this, the derivative of u with respect to x will be 12x cubed minus 1, which is this guy here. And now the only thing we need to do is just replace the function. You'll see u of x is right here, right? Again, this is u of x is right here. And this is nothing. The whole thing here is the derivative, u prime of x. Okay, let me write it again. So that, it's just the same example. This time, instead of tangent, it was secant. Does this make sense for everybody? Any questions so far? No questions, so okay. Well, I always think if there are no questions, I would like to assume that you got it perfectly. It's like it's crystal clear. I would like to, but I don't want to lie to myself, but anyway, I will assume that. Hopefully that is the case. All right. You want to see more examples? I'm sure deep down inside you want this. So I'll go with more examples. Let's see. This time I'll change a bit. So probably you got sick of that degree 4 polynomial, so I'll change a bit. Look at this. So I need to find the derivative with respect to x of cosine of x squared over 5x cubed minus 6x. You see, here something happens. So I have a, anyway, I'll let you think about it for a minute or two. So we need to clearly identify the functions. And I look at the interpreters, poor guys. I hope I don't give you too much headaches, I hope, right? Okay, okay. Because it's not like a literature class where I have to talk with mathematics and everything. So probably is it more difficult for a math class than any other class?
I would say it's about equal.
Ah, equal. Okay, okay.
Different challenges.
Ah, different challenges. Okay. All right, let's see. So which one is the inner function? Which one is the outer function? So u of x is what? So let's see, Jasper here, the inner is exactly. So the inner will be x squared over 5x cubed minus 6x. And let me see here, f of u, the outer function will be, let's see. Okay, and the outer function will be cosine of u, correct. Okay, so we need to find the derivative of this, all right, but now here we go. How are you going to find the derivative of u of x? What are you going to use? You see, you have a fraction there. So what are we going to do in this case? Well, the quotient rule, exactly, like Jake says, quotient rule. Oh, so let me write it here. We can compute it separately. So u prime of x is nothing else than just x squared over 5x cubed minus 6x. Everything prime. So this guy will be by the quotient rule. So let me write it here. Right, the quotient rule. This guy will be x squared prime times 5x cubed minus 6x minus x squared times 5x cubed minus 6x, everything prime, and everything over 5x cubed minus 6x, and everything squared. Okay. All right. So we computed the derivative of the, oh, wait, let's go with the computation. So this will be 2x times 5x cubed, man, what a mess, minus 6x minus x squared times, and the derivative of this guy will be 15x squared minus 6. And everything over, I hope you can you can see everything in this mess here. 5x cubed minus 6x, everything squared. Okay, I'm just gonna circle it. All right, now let's look here. We applying the chain rule, right? And we know how to compute the derivative of this. Oh, let me write it here actually. So this is 2x times 5x cubed minus 6x minus x squared times 15x squared minus 6. Ugh. Everything over 5x cubed minus 6x, everything squared. All right, so that's, I hope you can see that mess over there. Can you guys see it? On the screen? Okay, that's good. And now, what is the derivative of cosine? Is negative sine of u. Okay, great. So I have this guy here. I have this mess here. Beautiful. Guess what? I apply the chain rule. Yes, like Muhammad says, yeah, exactly. And look what we got. Well, let me just say the derivative of, so here I apply the chain rule. So I'll get the derivative of cosine of u is this guy. And here, and this guy will give me this guy. And here I'll apply the quotient rule. We already computed this. You see it's the same thing as this guy here. They're pretty much, well, exactly the same. And now I'm just going to replace by the function u. Do not forget who my function u is. Look at it here, right here. Oh. See it here? U of X. And guess what? You will see it here. And here, I will leave it to you to do the algebra. I don't want to do it. Whatever. So this is just the same thing as this. So this is U prime of X. All right, so this was a bit, well, because you need to apply two rules. But now, let me give you something even more complicated. And pay attention here. Because we will have three functions, and I would like you to identify these three functions. Again, this is the chain rule. But this time, we don't only have two functions, we have three of them. We can have even more, we can have four, we can have five, but you know, once we have two and we know how to take the derivative, then we can have more. We can apply the chain rule over and over and over again. So I would like you to look at this. And this time, I would like you to identify who is V, who is U, who is F.
F is equal to tangent of U.
Say that again.
F is equal to tangent of, or F of U is tangent of U.
So F of U is tangent of U, okay. What else? Who is V? U of V, pay attention here. It's a bit tricky. U of V will be what? Because you see, I have the tangent, I have the square root, and I have 3x squared minus x plus 2. So we have three functions. So let's identify them.
Would it just
I
be
would
the
like to
inside function?
say that. So U of V will be, we'll say that again.
The inside function?
And somebody says here, Josh says will be the square root of V, correct? So U of V is square root of V. And who is V of X? Is in what you said earlier is the inside function. So basically we have the following. You see? So first we take the tangent. So it's the tangent of the square root, right? So the square root would be V, and then at the end would be U, and then at the end will be V. Because it's F of U of V. Do you understand what I'm saying? So I have F of a function which is the composition with another function. So it's F of U composed with V. It's F of U of V of X. I hope this won't give you any headaches. But yeah, probably it's a first for you because you'll be like, oh my, what the hell is going on here? I have three functions, not just two. Well, trust me, the situation can get even worse than this. I think one of my, when I first taught Calc 1, I think, but that was in fall 2019 here at Tech. Oh man, I give them, and probably you have seen the exam, the Gateway exam, the Gateway 1 exam. That was a difficult one. Poor guys. But you will see, I think I gave the composition of a function, the last example, I think it was like 4 or 5 functions. It was a mess. But anyway, you know how it is the first time when you teach it, you tend to exaggerate. And then when I saw the results, I said, okay, I'm not going to give these kind of examples again. But you see, this time, we only have three, the composition of three functions. All right, so now let's apply the chain rule. Again, you will see the chain rule applied, well, as you can see there twice. So that's the derivative we would like to find out, right? With respect to x, so it's this guy here. So this guy will be equal to, by applying the rule here, right? That will be the derivative of the tangent of u with respect to u, which we know how to compute, times the derivative of square root of v with respect to v, which we know how to compute. And at the end will be the derivative of v with respect to x, which we know how to compute. So let's write each and every one of them right here. First of all, what is, okay, here. What is it? F prime of u is what? What is the derivative of tangent? Is secant squared. All right, now let's see this other one. What is the derivative of this? We have previously seen u prime of v is what? What is the derivative of square root of v? Is what? It's 1/2, exactly. So it's 1/2 v to negative 1/2. Great. So I have this guy here. I have this guy here. And what about this guy here in red? So this guy, v prime of x, will be what? Let's put it here. Is 12x cubed minus 1. Okay, so I have it here. Now let's put everything together. Oh my, so I'm. And guess what? We will obtain this. I'll go a bit over time because I want to finish a bunch of examples. So as you can see, this guy is right here. Look at this guy here. This guy is right here. Look at it here. And now in red, this guy is right here. And now I just plug it in. You see here u of x. Again, you will find here u of x because v is also a function of u of v, right? And here you have the derivative. So this is the final result. All right, a similar example, let me just, with again 3 functions, is this guy here. So let's see, who is v, who is u, who is f? Tell me. So let me just quickly say, look at this guy so we can identify. So again, this is the chain rule here for 3 functions. Right? So v of x we can identify. V of x will always be this guy inside here. Then u of v will be the square root of the guy inside. And then the whole thing will be the exponential. And again, by applying the chain rule, guess what? And I'm gonna go directly, show it to you. Will be this. The derivative of this, you know how to compute it, right? It's e to the, so the derivative of this is this. Then we have the derivative of this guy, just like we previously seen, would be this. And again, the derivative of this guy is this. So now we're just going to replace it here. This is u of x. Pay attention, this guy here inside. Again, you can now observe it here as well. And this will be the derivative. So in other words, it's just the chain rule, right? So the chain rule that you guys see here, boom. Right? All right, there is another example, and I'll leave this to you as a homework because I'm a little bit in a hurry. Look at this guy. So we need to compute the derivative of this. As you can see, look at this guy here inside. So that's the function. So again, you need to identify three functions here. You need to identify which one is f of u, which one is u of v, and which one is v of x, right? And in this case, if you look, v of x will be what? Will be the guy inside, so will be x squared plus 3. U of v will be cosine of v, and f of u will be 1/2 u cubed, right? And now we're just going to apply the chain rule. It's the same thing again. Okay, I'm just going to show it to you, and I'll leave it to you to figure it out. The only thing I'm going to mention here is just look at the derivatives. Look at this guy here. You can identify as this guy, right? Also, look at this guy here in green. You can identify as this guy because we know that the derivative of cosine of is a negative sign. And also at the end, this guy here is just this guy because the function v of x, the derivative is just 2x. And then you just plug it in, right? Okay. Also, let me show you another example. All right, which can be formulated in this way. Where does this function, right, e to the power x to the fourth minus 8x squared have a horizontal tangent line? What does it mean, a horizontal tangent line? Can you remind me this? I forgot. What does it mean? What does it mean for a function to have a horizontal tangent line?
The slope at that point is 0.
Which means?
It's like a change in direction.
Oh, okay, be more specific.
The entire thing would be equal to 0.
The derivative will be 0, exactly. So horizontal tangent line means that the derivative with respect to x is 0. Okay, so again, we need to identify this time two functions, right? Because we have e to some power, and again, we will apply the chain rule. Look, use the chain rule for u of x is x to the fourth minus 8x squared, so the function inside. So this guy is u of x, as you see it here. And f of u will be nothing else than just the exponential, so e to the power of u. And again, by applying the chain rules of the usual, you'll get this, right? So you see now, this is the derivative here. Look at this guy. This is e to the power u. And here we will have u, the derivative of u of x, the derivative of u, right, with respect to x is this guy. So now you see it here, u of x, and here you see the derivative. Again, just the chain rule. Chain rule. You already see the rule here, look. Right. This time we have two functions. And now the only thing we need to do, well, we want to see is not over because we need to solve this equation. Look at this here. The derivative of this function to be 0. And guess what? The only thing we need to solve because, right? So this guy is 0, so this equation, the derivative of this is 0, right? We compute it here, right? But the exponential will always be positive. So the only thing we need to come up with that will result is that this guy is 0. So this guy is 0, as you can see it here, you can factor 4x even. And then you'll get 4x times x squared minus 4. You can also factor x squared minus 4 as x minus 2 times x plus 2. And then guess what? You only have, so this will be 0, this will be 0, or this will be 0. And it will resolve that we have these three cases. So When, to answer the question, when does this function e to the power x to the fourth minus 8x squared have a horizontal tangent line? Well, the answer is when x is 0 or x is -2 or 2. Okay, I know I'm a little bit over time, but I have one more slide, and this is a very conclusive slide. Well, in this case, I want you to pay attention to this slide here, because at this point, we can, based on the chain rule, we can have the extended derivative formulas for all elementary functions. For example, you know, for the power function, as you can see it here, right, is the same thing as n times u to the power n minus 1 times du dx, right, the derivative, right? You can write this as u to the power n prime is n times u to the n minus 1. Pay attention, this u is a function of x, and I'll put it here so that you guys can see it. U prime of x, always going to be like that. And the same goes for the second one, for the third one, fourth one, whatever, right? So the only thing, so you take any rule. So you say, okay, let me take the derivative of sine. You know that sine of x, usually when you have the variable inside just x, it will be the cosine of x. Okay, but you don't see that. It's cosine of x times 1, which is the derivative of x prime. But if you take, for example, instead of sine of x, you take sine of u of x of another function, then you'll have, it will be cosine of u of x times u prime of x. So for any elementary function, do not forget that using the chain rule, I'll have this extra u prime of x, so the derivative of the function inside the whatever it is there, sine, cosine, ln, and so on. So I would like you to look at this, look at it for a bit. And you will see that you will always identify this guy here, u prime. You look at it everywhere. But the function in front of this is just the usual function, the usual derivative of whatever function you're taking the derivative of. So I would like you to look at this, and hopefully you'll get, once you see the video, I'd like you to have a very good look at this, because this will be very, very, very important when you take the derivative of composite functions. Okay, with that being said, I think I'm going to stop here. So this is, like I said, it was a very, very important lecture. Next time I will use this chain rule to do an implicit differentiation. So stay tuned. More material is coming. So I'll see you. I have office hours in 6 minutes, so you're welcome to join anytime. Okay, I'll see you. Take care. Bye-bye.